This is the 26th lecture of my series on advanced mathematical physics, in which we are studying differential geometry. Over the last few lectures, we have been looking at differential forms, and in the very previous two lectures, we have actually taken a look at an operation that you do on differential forms to produce a higher order form. This is the exterior derivative of a k form omega. The exterior derivative is d omega, which is a k plus 1 form, which is defined by this rather non-trivial looking expression. In the last lecture, we had shown that this actually is a k plus 1 form because it maps k plus 1 smooth vector fields to a smooth function, and it does so both R multilinearly and C infinity multilinearly. Hence, it's a smooth tensor field, and it is completely antisymmetric in all its arguments. All these go together to prove that this is a k plus 1 form. We had also earlier proven, assuming that this is a k plus 1 form, that there is a simple expression for this. If omega is written in terms of components, when you are using a coordinate system given by x1, x2 up to xn, in this particular manner, then d omega is simply the exterior derivative of the function omega, which is nothing but its differential, wedged with the rest of these coordinate differentials. Or, written a bit more explicitly, this is given by the partial derivative del omega I1 through ik del xj dxj, which of course is nothing but d omega I1 through ik, wedged with the rest of the coordinate differentials as they stand. Remember, the wedge product for odd order forms, in particular for one forms, is antisymmetric, so the order in which these differentials stand is actually quite important. Now, this particular result is extremely important because much of the calculations that we can do with differential forms can be done much more simply using this kind of expression. As you can easily see, that this is a much simpler expression than the coordinate independent definition that we had given. And also, some of the proofs that we are going to take a look at today are much easier to do using the coordinate based expression. As I have already said before, the proof that we gave for this expression is something which I personally don't like that much. It had assumed beforehand that this d omega really is a k plus 1 form. Once we have actually proven that d omega is a k plus 1 form, that gap in that proof had already been plugged. However, I would still say that this is not the best way of proving this particular expression, and I'm going to give you a much simpler proof now. Before we prove this in another way, we need to establish one important result about the exterior derivative of a k form, and this involves the exterior derivative of the product of a function and a k form. Of course, when you multiply a function by a k form, the resulting thing is also a k form. The question we are asking right now is what happens when you do an exterior derivative of a product f times omega. How is that related to df and d omega? Now, to figure out exactly what d of f omega is, we will fall back on the definition of the exterior derivative. So we have k plus 1 times d of f omega fed all these k plus 1 vector fields given by these two sums on the right hand side. Here, all we have done is replaced omega in the definition by f times omega, here and here. Now, it's very easy to see that this term is f times what it would have been if omega had been there alone. However, there is a bit of a problem with this. This is xi acting on the function f times the function given by omega acting on this bunch of arguments. And using the fact that a vector field acting on a product of functions as a derivative property, this splits up into two terms. One of which is f times xi acting on omega x1 through xk plus 1, which along with this term gives you f times exactly what d omega did when it acted upon x1 through xk plus 1. However, you have one more piece left, which is where xi acts on f, and that's multiplied by omega acting on the rest of the arguments. Of course, the whole thing is multiplied by minus 1 to the power I plus 1 and summed up over all I running from 1 to k plus 1. So in addition to this piece, which is basically f times d omega acting on these arguments, you have one extra sum left, where xif gets to act on omega times the rest of the arguments, and the whole thing is weighted by an appropriate sign and summed over. The question really is, how do we identify this term? And in order to facilitate that, we are going to give it a name. This whole term is some object theta acting on x1 through xk plus 1. And the whole question is exactly what is this theta? Now, one important thing to note is we have already established that exterior derivative of a k form is completely antisymmetric, being a k plus 1 form. So, here, on the left, d of f omega is completely antisymmetric in these arguments. In the first term, you have f times d omega acting on these arguments, which again is completely antisymmetric in all of these arguments. And that means that the remaining term, our theta, is also completely antisymmetric on all the arguments. Simply because it's a difference of two terms which themselves are completely antisymmetric in each of the vector field arguments. Now, because theta is completely antisymmetric, if you apply the alternator operator on that, you must get theta back. This is going to be crucial to our proof. But before we try identifying exactly what this term means, in general, let us take a look at a simpler case. The simpler case that we are going to look at is a case where omega is a 2 form. So k is 2 and d omega, of course, is a 3 form. So our theta will also take 3 arguments, x1, x2, x3, and this is just a definition of our theta, just this sum up here. The only difference here is that here we are choosing k to be 2, so the sum goes from 1 to 3. So this is an easy enough sum to write down. You will get x1 acting on f times omega x2 comma x3, x1 gets dropped, minus x2 acting on f omega acting on x1 x3 plus x3 acting on f omega x1 x2. The plus minus plus signs are simply the alternating sign here, and in each case you started with the argument list x1, x2, x3 and dropped x1, x2 and x3 in succession. So this is what you have. Now, let's just realize that a vector field acting on a function is the same as differential of the function, this covector field or one form acting on the vector field. So this is df x1, here you have df x2, here you have df x3. So falling back upon the definition of the tensor product of two tensor fields, you have df tensor product with omega with arguments x1, x2, x3 sitting here. This is df tensor product with omega with arguments x2, x1, x3, and this is df tensor product with omega with arguments x3, x1, x2. With, of course, the plus minus plus signs still intact. Now we make use of our result. Theta is the same as the alternator operator acting on theta. So curly A theta acting on x1, x2, x3 is simply curly A acting upon these. But curly A acting on df tensor product omega is nothing but df wedge omega. So we have df wedge omega acting on these three pieces. So the arguments here are x1, x2, x3 here, x2, x1, x3 here, x3, x1, x2 here. And note that I can make the argument list of all these three terms exactly the same by making use of the fact that now that we have the wedge product of a one form df and a two form omega, each of these is essentially the same tree form and it is completely antisymmetric in its arguments. So this term, let's leave it as it is, but we can give it the same set of arguments by interchanging x1 and x2 here, or simply making x2 jump back one step. Since x2 has to jump back one step, one interchange, one minus sign, so this becomes plus. So these two terms are actually exactly identical. Now notice that here, if we wanted the same sequence x1, x2, x3 of vector fields, x3 would have to jump over x1 and x2. Two jumps, two interchanges, minus 1 whole square factor, so plus sign. So what turns out is that each of these three are exactly identical and they're each equal to df wedge omega acting on x1, x2, x3. So theta acting on x1, x2, x3, which is of course the same note as alternator of theta acting on x1, x2, x3, is the same as 3 times df wedge omega acting on x1, x2, x3. Our case at least, theta is 3 times df wedge omega. Now let us try to see whether this actually works in general. That is, for an arbitrary k form. The argument that we will use follows along exactly the same lines. Oops, I have made a small mistake here. This of course is 3 times df wedge omega. I believe I said that, but while writing I dropped the factor of 3. Now, in the general case, we will have theta fed a bunch of k plus 1 vector fields as arguments. As we have argued, this must be the same as the alternator acting on theta fed with the same bunch of arguments. And here all I have done is written out theta explicitly in the form of this sum, where you have df xi and omega with a bunch of arguments which is x1 through xk plus 1, but with the xi dropped. Now, notice that this is of course the same as the tensor product of df and omega acting on the bunch of arguments which has xi at the beginning and then comes x1, x2 up to xk plus 1 with xi being dropped from here. But now, let's apply the alternator on the individual terms, which is a legitimate thing to do. After all, the alternator is a linear operation. Doing it on the entire sum is the same thing as doing it on individual terms and then summing up. So you have an alternator of df tensor product omega sitting here, but that by definition is a wedge product between df and omega. So in each and every one of these k plus 1 terms in this series, you have a factor minus 1 to the I plus 1, so a plus minus factor. Then df wedge omega acting on almost the same bunch of arguments, the difference being that in the ith term of the sum, xi has been brought to the beginning. But you can give these exactly the same set of arguments just by making xi go back exactly here. But in order to go back here, it would have to jump over x1, then x2, then x3 and all the way, finally over xi minus 1. That is, it will have to jump over xi minus 1 arguments on its way. I minus 1 interchanges, a factor of minus 1 to the I minus 1 would come over with xi back at its original position. So what you will have is minus 1 to the I plus 1, which you already had, times an extra factor of minus 1 to the I minus 1, which of course is minus 1 to the twice I, and that is always plus 1. So we find that written in this form, each and every one of the terms in this sum, each and every summand is one and the same. df wedge omega acting on x1, x2, x3 all the way up to xk plus 1. Since each of the terms in the sum are the same, the sum is simply the number of terms k plus 1 times each term, df wedge omega acting on the bunch of arguments. Now let's get back to our original expression for d of f omega. What we have seen already is that k plus 1 times d of f omega acting on x1, x2 up to xk plus 1 is k plus 1 times f d omega acting on the same bunch of arguments plus theta acting on the same bunch of arguments, and we have just shown that theta is k plus 1 df wedge omega acting on the same bunch of arguments. So cancelling out the k plus 1 common factor from both sides, and given the fact that you are using exactly the same bunch of k plus 1 vector fields on both sides, we immediately end up with this very important result. The exterior derivative of a function times omega is the function times the exterior derivative of omega plus df wedged with omega. This formula is going to be exactly what we are going to make use of to derive our coordinate-based expression for d omega very, very quickly. And that is what we will turn to next. Just one quick result before that, a rather trivial one almost. If you were to take the definition of the exterior derivative and there replace the omega everywhere by omega 1 plus omega 2, it's easy to see that the whole expression would split into two pieces, and from that it follows rather trivially that d of omega 1 plus omega 2 is d omega 1 plus d omega 2, and indeed this can be easily extended to multiple such k forms, say n such k forms added together, and result will be the exterior derivatives of each individual k form finally added together. Now I will need this result simply because the basic form that we use in coordinates, that is given a chart u, phi on M with coordinate functions x1 through xn, omega can be written down in this form. This is really not just a product of a function with a k form, but a sum of many such products. So we will use this result that you can split up a sum on which an exterior derivative acts, and then use the fact that each individual term in the sum is really a function which belongs to C infinity M and a k form. And there I am going to use our formula d of f omega equals f d omega plus df wedge omega. So making use of that, it follows simply that this whole thing is going to split up into two terms, or rather two sums, because each of these are of course summed up over I1 through Ik. And following our formula, we get d of omega is d omega I1 through Ik. Of course, this is d of a function, wedged with the rest of the k form, plus omega I1 through Ik d of this expression. Now, it is very easy to see, if you go back to the definition, that this term is going to actually vanish. To see that, all you need to do is take this d of this k form, feed it k plus 1 coordinate differential vector fields as arguments, and then just use the definition. As usual, the definition splits up into two sums. You have del xjn, the nth term here, coming out with the k form acting on the rest of the arguments is minus 1 to the n plus 1 here. I've just used n rather than I as the index here, and n runs from 1 to k plus 1. And a double sum where m and n play the role of I and j in our definition, minus 1 to the m plus n, the k form dxi1 with dxik acting on the Lie bracket of del xjm and del xjn with all the other vector fields in the original sequence following that up. Now, it's a very standard result that we had proven long ago, that the coordinate differential vector fields commute in the Lie bracket sense. That is, if you calculate the Lie brackets, you get a 0. And this being a K form, it's also, of course, a K tensor, 0 K tensor. And if any one of its arguments is 0, multilinearity guarantees that each and every one of the terms in this second sum is 0. What about the first sum? Well, the first sum has the coordinate differentials acting on the coordinate differential vector fields in some combination, then using a permutation of the arguments with plus or minus signs and so on. But the important thing is, when dxi1 acts on, say, del del x j1, that's the same thing as del del x j1 of xi1. That's either 1 or 0, a constant function always. And any of these linear combinations which come in because of the wedge product is ultimately going to be a constant function which vanishes when you hit it with del del x jn. So ultimately, each and every term on the right hand side here vanishes and you get 0. Since this gives you 0, acting upon any arbitrary bunch of coordinate differential vector fields, and any vector field can be written down in terms of these coordinate differential vector fields times functions, it follows that this exterior derivative of dxi1 through dxik is actually 0. And therefore, going back to our expression for d omega, this second term vanishes and you are left with just the first term, which of course is what we had derived before, but with a lot more effort. Now, the formula that we have derived right now should remind you of the formula for the derivative of a product of two functions. So you might wonder whether this is why you call this the exterior derivative just a derivative. Well, apart from this, you of course have the fact that if the form in question happens to be a 0 form, then df, the exterior derivative of a 0 form, is nothing but the differential of f. So in that case, the exterior derivative operator d plays exactly the same role as an ordinary differential operator. Well, as we have just said, the differentials of ordinary functions obey this property, which is called the Leibnitz property. And the formula that we had derived right now d of f omega is f times d omega plus df wedge omega looks very much like this. In fact, it will look even more like this if you were to remember that if you are doing a wedge product between a function and a k form, that is simply the same thing as multiplying the k form by the function. So this is really f wedge omega, and f times d omega is also simply f wedge d omega. In this particular version, this formula looks exactly like the ordinary Leibniz property. But remember, here we have f, which is explicitly a 0 form, and omega, a k form. We might be tempted to ask if instead of a 0 form and a k form, we had a k form and an L form taking part in the wedge product here, would you have a similar property? We don't really have the same property, but we do end up with a very similar property, something which is called the graded Leibniz property. So, here we are talking about the exterior derivative of the wedge product of two forms, one k form omega and a L form eta. The best way to derive the graded Leibniz property is make use of a coordinate representation. So in this and the other proofs that I'm going to do today, I'm going to assume that we are using a coordinate system, and therefore we can make use of the standard property of the exterior derivative written in terms of coordinate differentials. To begin with, we write both omega and eta in the coordinate version. That is, write omega as omega I1 through ik multiplied by dx I1 wedge dx I2 all the way up to dx ik, and eta in the form eta j1 through jl dx j1 wedge dx j2 all the way up to wedge dx jl. Now we make use of the fact that the wedge product is associative and also linear to pull the etas out and put them together with the omega. So you have omega I1 through ik, eta j1 through jl, then you have the bunch of the coordinate differentials being wedged together in exactly the same order as they appear here. Once again, remember, with coordinate differentials, which are one forms, wedge products are anti-commuting, so the order has to be maintained carefully. We are going to do a d of this whole expression, which is a function, namely omega times eta, multiplied by a bunch of dx's wedged together. So we can now make use of our formula that we had derived to write the coordinate differential of this as simply the differential of this product function wedged with the rest of the coordinate differentials which sit here. Of course, you must have already figured out that I am writing the terms which come from omega in orange and those which come from eta in purple here. So, here you have omega times eta, the component functions being multiplied together, and then you have these which were originally in the expression for omega, and then these which were originally in the expression for eta. Now, this is a product of two ordinary functions, and for them d is just the ordinary differential, and therefore this obeys the standard Leibniz property. This is d of omega I1 through ik times eta j1 through jl added to omega I1 through ik times d of eta j1 through jl. All this wedged together with the dxi's, I1s through dx jl. Now, let's split this up into two terms. The first term here comes from this wedged with this, and the second term here comes from this term wedged with the rest of the basis vectors. Notice that here I can move the eta j1 through jl, which is just a function, directly back here. And you are going to end up with d omega I1 through ik wedged with dx I1 wedge dx I2 up to wedge dx ik at the beginning, and that is just going to give you the d omega. And when eta j1 through jl gets coupled with this, you end up with eta. So the first term here is obviously d omega wedge eta. So d of omega wedge eta is beginning to look very much like the standard Leibniz property. It's d omega wedge eta plus something else. Now, we have to be a bit more careful. With that something else, here also, you will have the omega. In fact, you already have the omega. Omega I1 through ik dx I1 wedge dx I2 up to wedge dx ik. That would be omega. And if I could move the d eta from here back so that it sits here, then I would really get the eta overall. But there is a catch. Note that here I could move eta back here without any other effect because eta was just a function. But here we are trying to move d eta, which is a one form. And one forms anti-commute as far as the wedge product is concerned. So moving the d eta j1 through jl all the way back here would actually require you to jump over all these coordinate differential one forms in between. In fact, exactly k of them, dxi1, dxi2 all the way up to dxik. And that means that you will have to do k interchanges, and that in turn means that what you are going to get is a factor of minus 1 to the k. Now once you have done that, as we have already said, this is nothing but d omega, and this is of course eta, and here you have omega and here you have d eta. So what we end up with is d omega wedge eta, as we have already said, but we don't really end up with omega wedge d eta. You end up with minus 1 to the power k times omega wedge d eta. The minus 1 to the k coming from the fact that this d eta j1 through jl has to jump across k dxs to get here. So this is our graded Leibniz property. Let me just write that down once again. If omega and eta are k forms and l forms respectively, your d of omega wedged with eta plus minus 1 to the power k omega wedged d eta. So whether it's going to look like the ordinary Leibniz property or not depends on whether omega is an even order form or not. Note that the special result that we had already derived before, that about the function f, obviously obeys this. F being a zero form, the sign factor in the second term there would be minus 1 to the power 0, which is of course plus 1. So for a function and a k form, you will always get d of f times eta or d of f wedge eta equals df wedge eta plus f wedge d eta. But you have to be careful about this. If the rank of the first factor in a wedge product is odd, then the exterior derivative does split into two terms, but it has a minus sign between the two terms, not plus. This fact that you get a plus or a minus sign depending on the rank of the form that is being used is why you call this a graded Leibniz property. Let me now stress something which should be perfectly obvious in the first place, that if we were to interchange the two forms here and work out d of eta wedge omega instead of d of omega wedge eta, you would get something very similar, but the result would be something like this. Minus 1 to the L eta wedge d omega. Now what we can do is do a quick consistency check between these two. Strictly speaking, this consistency check is not really necessary because we have already proven this expression. So they had better be consistent with each other. However, we can try to use the fact that we know the relationship between eta wedge omega and omega wedge eta. They are not necessarily equal to each other. There is a factor in front which is minus 1 to the kl. Let me remind you that the wedge product is commutative if any one of the two forms or both are of even order. If both of them are odd rank, then the wedge product anti-commutes, which of course is something we have been using so far. If you have two one forms, their wedge product definitely anti-commutes. Now, using this, let's try to figure out d of eta wedge omega from the d of omega wedge eta. So that's minus 1 to the kl d of omega wedge eta. That's minus 1 to the kl omega wedge d eta plus d omega wedge eta, but there is a minus 1 to the k in this piece. And now let's try to rewrite these two terms exactly in this form. Of course, here you want the eta to come in front. So we have minus 1 to the kl. Let's tackle this term first. You want to switch the wedge product and get eta wedge d omega. But now you have to remember one thing. The factor that you get when you switch the two forms in a wedge product, that depends on their individual ranks. Now here the two forms which you are switching are not k and l forms. They are k plus 1 and l forms respectively. So the factor you will get here is minus 1 to the k plus 1 into l. And what about this? Here you want to switch these two back, and these are a k form and an L plus 1 form respectively. So you get minus 1 to the power k into L plus 1 p eta wedge omega. So now the wedge products are exactly in the form that we want. All you have to do is pay attention to the factors in front. So here, when you compare these two, you get minus 1 to the k plus kl plus k plus kl from here. It's easy to see that it's minus 1 raised to an even power. So this is just eta wedge omega, as it should be. What about this? Here you have kl plus l. So you do end up with minus 1 to the l eta wedge d omega. So our consistency check works out perfectly fine. As I have already stressed, this was really not necessary, but it's nice to see that all the formulae that we are dealing with actually gel together rather nicely, and all the factors really fall into place. One more point. Sometimes people might find this formula a bit difficult to remember. Exactly what phase factor do you put here? One way to remember that is to essentially treat D as if it's a one form. So when D goes and acts on omega directly, of course it's sitting right next to it in this expression, no change necessary. But if D were to sort of jump across omega and go and hit eta, it's like you're interchanging omega and D, and because you have a one form and a k form, the interchange gives you an extra factor of minus 1 to the k. So you can think of D as something which is jumping across the coordinate basis one forms on the way. Since it's jumping over k such to get to hit eta, you are getting minus 1 to the k. In this expression, D acts on eta directly, so no sign for this. But when D goes and hits omega, it has to jump across eta, which is a L form. L coordinate basis one forms are sitting there, and that gives you a factor of minus 1 to the L when D jumps across all of them. This is just a good way to remember this result. We will now turn to an extremely important result which we had already hinted on when we first met the exterior derivative. We saw that when we applied the exterior derivative on a zero form twice, that is, apply it on a zero form to get a one form and then apply it on the one form to get a two form, that two form vanished identically. We had also shown that if we did this to a one form to begin with, to apply D to it to get a two form and then D to it again to get a three form, the resulting three form also vanished identically. What we want to show now is that this result is actually universal. D applied twice on any form will make the result vanish. In other words, D square vanishes and D is what is called a nilpotent operator. Something which when you apply twice, you end up with a zero. This result is extremely important and you will see many applications of this as the course progresses. But for the time being, let's try to prove this result. Once again, the proof is very, very simple if you use the coordinate version of the formula for the exterior derivative. So let's try to see that. We start, of course, with the by now standard expression that d omega is del xp omega I1 through ik dxp, that is d of omega I1 through ik, wedged with dxi1, wedge dxi2 all the way up to wedge dxik. Now this is a k plus 1 form. We want to do d on that once again. Note that the coefficient function for the k plus 1 form is simply this partial derivative sitting here. So when you do d2 omega, you do essentially d of this wedged with the rest. So del xq of this quantity dxq, that's d of this quantity wedged with all of this. So what you end up with is the second derivative with respect to xq and xp of omega I1 through ik, dxq wedge dxp, then it's followed up by dxi1 wedge dxi2 up to dxik. original set. All of these are K's. Now comes the point. Q and P are both summation indices here. So if you interchange the two, nothing should change. Let's see what happens when you interchange the two. This becomes del xp del xq, and here you get dxp wedge dxq. All the rest, of course, stays the same. But note that a partial derivative of a smooth function, this mixed partial derivative, is the same under an interchange. So this is the same as this with a plus sign, exactly the same as this one. Whereas dxq wedge dxp and dxp wedge dxq are actually negatives of each other, being the wedge product of 2 1-forms. So you get minus sign here. What that means ultimately is d square acting on omega is negative of d square acting on omega, and the only thing which is the negative of itself is of course 0. So d square acting on any k form gives you 0, and as a result d square as an operator vanishes. D is a nilpotent operator. This will actually turn out to be extremely important. So important indeed that it will give rise to an entirely independent branch of topology, something called de-Rham cohomology. We may study this if we get enough time. Now, de-Rham cohomology might sound like something very esoteric, but we have actually already seen this expression in action. D acting on a function essentially gives you del f del x dx plus del f del y dy plus del f del z dz. It gives you a one form whose component functions look like the components of a gradient. Doing D on a one form, as we have seen before, essentially reproduces the curl. Doing D twice on a function gives you 0 is something we all know from ordinary three-dimensional vector spaces. That is, curl of a gradient of a function is 0. Very similarly, if you start with a one form in three-dimensional space and apply D twice on that, the resulting 0 that you get essentially tells you the divergence of curl of a vector field is 0. So d square equals 0 is really something we have all seen at a more elementary level. Here we are actually getting to see that in a much more general setting. We will have a lot to say about differential forms and their applications in these lectures. But the next lecture will be slightly different in tone. We have already hinted at that in an earlier lecture. I would like to show you exactly why the coordinate independent definition of d omega takes the form that it does. In other words, we will try to derive for ourselves the expression for d omega. That is something which I have not found in any of the textbooks I have consulted. But the proof is pretty straightforward, though it does take some time and effort. That is what we will devote our next lecture to. Bye for today.